So I think we can start now, Carlos.
Wait, yeah.
Yes.
Yeah.
Would it be okay, David, if we?
Yes.
So I'll just make a brief announcement of the talk. So thank you everyone for coming. Welcome to this new session of our category seminar. We're very happy to introduce today's speaker, David Spivak from the Topos Institute, who will be speaking to us about polynomial functors and their applications. We would like to encourage everyone to make questions at any time during or after the talk. So these questions can be asked in Spanish as well. In that case, we would be very happy to translate for David. There will be time for discussion after the talk, and we would like to encourage any questions or comments during that time. So yeah, please, David, take it away. Thank you very much.
Okay, thanks, Juan, for inviting me. It's a pleasure to be here. And yeah, so I'll start with some personal history and then I'll move into some math. And then Juan encouraged me to not make this like my previous talk, which is all math. If you want to see that one, it's on YouTube. But to talk about some kind of speculative directions for, where we could go with from here and stuff like that. Okay, so my personal history with math was, I wasn't like a math competition person. I was more just like a math, like math is going to solve my life type person. I thought that I could understand like myself and life and the world with math. And so we generally share experience and knowledge in natural language. We talk to each other. But it seemed like, well, if I can say circle in math, why can't I say I'm hungry in math? Or I need food or whatever. So is anything that we want to talk about that's actually, informative or real in some sense, is it precluded? Like which things are precluded? In other words, not possible to say mathematically, or maybe everything is. So what are the lines there? Let me see. Okay, so when I learned category theory, CT, I thought, okay, this is where I can finally say everything. It's this sublanguage of math that can talk about math itself. And it's a clean and principled and structural and expressive sublanguage of math. So I started trying to understand myself and life and the world in this language of category theory. And so what can you say about self and life and world? Well, to start somewhere, you usually have to make some assumptions. So I said, okay, let's just pretend that everything is all information and communication. So let's pretend that our mind is an information storage device, and somehow we communicate with each other and with reality. So our storage device of information communicates with other people's information storage devices and reality as an information storage device. Let's just pretend that. And so if we say that and we start to think of everything in those terms, it started to look like what people call databases and data migration. So my brain started to look to me like a database maybe. And I wondered, does that work? Can I think of everything that way? And the math involved was about categories and set valued functors from a category C to the category of sets, and what are called parametric right adjoints between C set and D set. And so that's the story that I started thinking about, and I'll go into this later. But the problem, I went to companies and I was telling them about databases using categories, but the companies would tell me about their processes, like the process for discovering new pharmaceutical drugs or something. And those interacting processes didn't fit nicely into the data picture. You can keep data about the process, but the process itself, where one thing happens after another and you can zoom into processes, didn't fit nicely. So then I started assuming maybe everything is just interacting dynamical systems, so processes and flowcharts. And it's just machines sending each other information all the way down. So maybe your computer involves a monitor and a keyboard, and you zoom into a CPU, central processor, and you zoom into the CPU and you see some adder circuits and some memory. You zoom into the adder circuits and you see logic gates, and all these little things, these little transistors or whatever they are just sending each other information. Or my brain is connected to my heart and my lungs, and they're sending each other data or information or stuff. And as long as we keep track of the fluids or the types of things that are flowing on the wires, we could understand the whole body in terms of whatever level of abstraction we wanted. But then the problem that came up to me was that, well, this works fine for a computer and a body maybe, but we did a project with NASA where these were airplanes. And the problem is the airplanes and the radars and stuff, they're not always connected and wired the same way forever. So sometimes one thing's wired to another, sometimes you're connected to Zoom, and sometimes you're not. And when you are, I send you information, and maybe I look at your facial expressions and you send me information. But when we're not wired together, it changes the wiring diagram. So then I got sad. Oh no, it's not this simple thing of just interacting with dynamical systems. And the point is, every time if we just try and see if it is just information and communication or is just dynamical systems, then at least we know where it fails. So I just want to keep looking and seeing where the next failure point is. But anyway, one day I met Poly, the category I'll tell you about today, and I fell in love. And so someone named Jonathan Laurent said, I'm polyamorous. It's a joke, but it seems about right. So basically, Poly captures dynamical systems and wiring diagrams that rewire. So based on where this wiring pattern can change as the airplanes move past each other or as we decide to connect to Zoom. But Poly, the category polynomial functors, is also just really well behaved. It's not ad hoc. It's kind of, it's been studied by a lot of people from a lot of different angles because it has a lot of great properties. And when I looked at dynamics in Poly, it seemed to be all about comonoids. And comonoids are something you can define in any monoidal category, but I asked my friend and colleague Joachim Koch about it, and he pointed me to Richard Garner. And Richard Garner's video had a hottest homotopy type theory electronic seminar talk, where he explained a result that said comonoids in Poly, these things that were all about dynamics, comonoids in Poly are exactly categories. Up to isomorphism, every category is a comonoid in Poly, and every comonoid in Poly is a category. And Garner also explained in his video that bimodules are parametric right adjoints. So if you remember on the previous slide, I said that categories and parametric right adjoints were the data migration story I'd found before. And it turned out that that was coming to me again from this other angle. I'd been looking at dynamics and found databases again. So all the stuff I'd been working on for 13 years suddenly came together, and I was overwhelmed or very, very happy with Poly's elegance and its capacity to be applied, both for dynamical systems and for databases. Plus, Poly is really computational. It's easy, it's hands-on, as we'll see. So you can really get your hands dirty with it without having to be too formal, but the formal properties are really nice. So today I'll recall some basics of Poly. Recall means I'll pretend you've seen it before, so I'll go kind of fast. Even if you haven't seen it before, I will start from the beginning, and I'll tell you about Poly, and I'll tell you how Poly models dynamical systems and databases. So I'll give some applications, and then I'll take Juan up on his invitation to be more speculative and discuss some open questions and speculations, and then I'll conclude with a brief summary. So that's the plan. So this category Poly, if you are, if you were an expert, I guess, you might call it many different things. You might say the following are all equivalent. The free, completely distributive category on one object. Completely distributive means it has sums and products can depend on sums, and they distribute over sums. Another way to say what Poly is the free coproduct completion, so freely add coproducts to set up. Another way to say what Poly is it's the full subcategory of all functors from set to set, spanned by those functors that preserve connected limits. So connected limits are basically everything but the terminal object in some sense. So pullbacks, equalizers. Or another way you could say what Poly is it's the full subcategory of all those functors from set to set, spanned by the coproducts of representables. And that's one we'll talk about today. And again, you don't have to memorize any of this because this is just to try to show you a bunch of different things that are coinciding on one category. In a second, I'll do a more hands-on way of looking at it. So another way to say what Poly is it's typed sets and collapse maps. So an object is a pair S tau, where S is a set and tau takes every element of S to another set. So it's a set of sets. That's all poly. Objects in poly are sets of sets. And a morphism, I may use this notation later a bit. A morphism from S tau to S prime tau prime is a function from S to S prime and a natural transformation going backwards. So it says, for every element of S, I get an element of S prime. And for every element of the corresponding set there, I get an element of the original corresponding set. But it's all here. I'll send the slides over later. So all the information is here and in various papers and stuff. But this will be simpler. So what's a polynomial? It's like y squared plus 3y plus 2. Something familiar. And we'll see that y stands for Yoneda, but you don't have to worry about that. It's just a polynomial like this. And there's 3 different views on it that I want to talk about. One is the algebraic view. One is the bundle view. So let's say you plug in 1 for y here. You get 1 squared plus 3 times 1 plus 2, which is 6. And that 6 will always just be, it's like the exponent doesn't matter. We're just going to add up all these little thingies here, 1 plus 3 plus 2, and we'll get 6. And those are the 6 things down here, 6 dots. And above the first dot is 2 elements. And above the next 3 dots are 1 element. And above the last 2 dots are 0 elements. So this was like y to the 0 is 1. And so the bundle view and this view are the same. I guess there are 2 different ways of expressing the same thing. And here's a third. There are 6 dots down here, and each one has, this one has 2 arrows, then 3 of them have 1 arrow, and 2 of them have 0 arrows. And so I'm going to talk about the things on the bottom here as positions. This polynomial has 6 positions. And for every position, it has some number of directions. The first position has 2 directions. The second position has 1 direction, etc. So that's terminology I'll use today. It comes from dynamical systems. When we apply these to dynamical systems, the positions will be points in space, and the directions will be kind of like the vector field, or like directions you can go. And the other application is categories. The positions will be the objects of the category, and the directions will be the outgoing arrows of the category. So the morphisms of the category that emanate or come out of each object. So yeah, I just said that each corolla, each little mini tree here is a position, so 6 positions, and the leaves are directions. Or we could say that every one of these is a decision and its leaves are options. This decision has 2 options, these 3 have 1 option. So if you're in a decision with only 1 option, you just got to go through it. And if you're in a decision with 0 options, you're done. You stop forever. And that's the one that we'll talk about for just a second longer. So what's a morphism of polynomials? Let's say P is y cubed plus 2y, and Q is y to the 4th plus y squared plus 1 plus 1, y to the 0 plus y to the 0. What is a map from P to Q? Well, it delegates each P position to a Q position and then passes back the options. So I could say, okay, I delegate my first decision to Q's first decision. I delegate my second decision to Q's first decision, and I delegate my third decision to Q's fourth decision. And then I say, okay, and the only one that really is interesting here is the first. I say, okay, I've delegated my decision 1 to Q's decision 1. And for every option that Q can pick, I'll tell you what it means. So I'll pass it back. So let's try an example. Let's say I could either have a decision to flip a coin, heads or tails, or I could have a decision to pick a number 1 through 6. And I want to delegate each of them to a card deck. So I say, okay, if I need to make my heads tails decision, what I'll do is the ace of spades will be, or the ace of hearts will be heads, and all of the other cards will be tails. And if I need to make a die decision, roll a number 1 through 6, I'll pick a card, and if it's 1 through 5, I'll pick that, and if it's 6 or above, I'll pick 6. And any way you could do that sort of delegation would be a map of polynomials. But mathematically, and this is what we'll concentrate on, is that poly is just sums of representable functors set to set. So for any set S, I'm going to write y to the power s, this kind of script y for Yoneda, to mean functions from set to blank. This is a functor. It takes a set and puts it in for the variable y. and it's the functor represented by S. And a polynomial is just a sum of representable functors. So the sum over I and I of y to the p bracket I. So this p bracket I is my notation for the directions in position I. A morphism of polynomials is just a natural transformation. And just to make things feel calm, plus really is the coproduct in this category, and times really is the product. So when I write y cubed, that really is y times y times y. In fact, it has exponentials too. So y cubed is actually also y to the power 3, where 3 is a polynomial that's constant. But that's not too important. So this is a very well-behaved category, plus times, it's Cartesian closed. It's got all sorts of monoidal structures. Just for notation, by the way, P, as I said, is going to be the sum over some indexing set. It's a sum of representables. And P brackets I is the name of the representable here. So the ith position has P bracket I many directions. But I want to note that I here is P of 1. If you plug in 1 for y, this whole thing just becomes 1 over and over and over, no matter what P bracket I is. So it's just this I many ones. And so I is P of 1. And so I can write this polynomial without any i's at all, just capital I's at all. Just I and P of 1 of y to the P bracket I. So this parenthesis 1 means I'm applying the polynomial functor to the one element set, whereas this bracket is just notation for the ith set of directions, the ith representing object. Okay, so let's talk about composing polynomial functors. If you have two polynomials P and Q, I'm going to denote the composite with P triangle Q. And why I don't use circle, I'll explain in a minute. So if let's say P is y squared and Q is y plus 1, then P composed Q just means plug in y plus 1 for y, so we get y squared plus 2y plus 1. And this is a monoidal structure. So you can do this with any two polynomials. You can plug one into the other, but it's not a symmetric monoidal structure because P composed Q is not Q composed P. If I plug P in for y of Q, I get y squared plus 1, which is different than P composed Q. The identity of this monoidal structure is y itself, because if I plug in y for y in P, I get P. And if I plug in P for y in y, I get P. So that's monoidal unit. And why I use this weird triangle symbol rather than circle is, first of all, if you're writing it on the chalkboard and you write this fast, it looks like a circle. So it's not a problem. It works pretty well. But I also want to reserve the circle for morphism composition. These P and Q, you might call them functors, but I'm thinking of them as objects. And so I don't want to compose objects. I want to compose morphisms. So this triangle, even though it is the composition of polynomial functors, since I'm operating it on objects, I chose a different symbol. But another reason for this triangle in particular is that it represents trees with P under Q. So it's like the tree is growing up from P to Q, and I'll show you that on the next slide. So suppose P is y squared plus y, and Q is y cubed plus 1. Then the composite P triangle Q is given by stacking Q trees on top of P trees. So you see all these Q trees are stacked on top of the P trees. It's like P is growing up into the Q. And so what I'm saying is that if you plug in Q for y here, if you take P composed Q, you will get y to the 6th, I'm counting 6, plus y cubed plus 1 plus y cubed plus 1. And so we can read off this composite just by stacking P trees under Q trees, and that's what this symbol is representing. It also looks kind of like you're feeding Q into P through this arrow. It's almost like you're pushing Q into P. And again, that's what composing means. We're plugging Q into P. So the notation I picked for those reasons. Now we're getting to the result that really made me fall in love with poly, which is that comonoids in poly are very interesting. So in any monoidal category, you can talk about comonoids. Whether you're in sets with times or whatever, you can say, what's a comonoid there? And a comonoid is always the same thing. It's a triple where you have this object M, called the carrier. you have this morphism from M to the monoidal unit called the co-unit, and you have a map from M to M tensor M called the co-multiplication. And what Ammann and Ustalu proved in, I think, 2016 was that comonoids, and they satisfy some rules, just like monoids do. But anyway, Ammann and Ustalu proved that comonoids in poly are exactly categories. So up to isomorphism, categories and comonoids in poly are the same. You can see their result, their 2016 paper, or if you want, which is all very computer science terminology based. If you want to see a talk where I explain it in detail, set theoretically, this is a link. I think you can find it on the Topos page, but I'll send these slides later. Okay, so how does this work? If comonoids in poly are categories, what's going on with that? Well, let me tell you how it works. So let's say C is a category, then what's the comonoid's carrier? What's the polynomial for that category? Well, what I'll do is I'll take the sum over all positions, the positions in this thing are the objects in C. And for every object in C, the directions there, the outgoing arrows are exactly the outgoing arrows in the category. So you take your object and you look at all the arrows shooting out of it, and that's the exponent there. The co-unit, this map here, assigns to each object and a certain map, which it turns out by the laws has to be the identity. And the co-multiplication from C to C composed C ends up assigning codomains to every morphism and composites. So when you put these things together, with the comonoid laws, it turns into categories. So comonoids in poly are exactly categories. But even though the comonoids are exactly categories, the morphisms are not functors. And that is weird. So a comonoid morphism, I'll draw like this because it's going to be a map in poly on the carriers. It'll go from the carrier of C to the carrier of D like a polynomial. So it'll go from so here's how it goes. For every object in C, if the object is called I, we do get an object in D called J, let's say. But instead of morphisms in C going to morphisms in D, they go backwards. For every morphism in D that emanates from J, we get phi sharp of F emanating from I. So it's forward on objects and backwards on morphisms. And it preserves identities, codomains, and composites. So let me give you an example. What's a cofunctor from C, an arbitrary category C, to the monoid of natural numbers? Well, the monoid of natural numbers under addition, 0, 1, 2, 3, etc., it only has one object. All the natural numbers are the morphisms. So a cofunctor like this on objects is trivial. It sends every object to the unique object. But on morphisms, it sends every emanating morphism here to an emanating morphism from an object here. So every object in C gets an emanating morphism, phi sharp of 1, assigned to the natural number 1. It also gets phi sharp of 2 and phi sharp of 3 and phi sharp of 0, but they're all determined by the cofunctor laws by what happens on phi sharp of 1. So it turns out that a cofunctor from C to the naturals is the following data. Imagine you have a category, and now to every object, pick one random morphism going out of it. When you do that for every single object, it looks like a vector field on your category. Every object gets an arrow going out of it, and that is a cofunctor from C to the naturals. And when I first saw that, I said, well, that's not what you do with a category. That's a very strange thing to do with a category. So cofunctors are kind of weird. And so it's a whole new world to explore. They're extremely natural because they're just morphisms of comonoids. So we can't say that they're ad hoc. We didn't make them to be weird. They just appeared and we haven't thought about them before. But again, in this case, it kind of looks like a vector field on the category, and that hints at applications, which we'll talk about in a few slides. But let me just say for right now, when I do pick one of these vector fields and another vector field, I can multiply them. So you actually get a monoid, a regular old monoid in sets of these cofunctors. So if you pick one and I pick one, then we can do yours and then mine and get a new one. So in fact, this is telling us that to every category you've ever heard of, there's an associated monoid of these vector fields. Okay, so now given comonoids in any monoidal category, there's something called a bicomodule. And what it is in poly is it's another polynomial M equipped with two maps, a map from M to C composed M and a map from M to M composed D. So it's like a left, if C is a category and D is a category, a bimodule is a left, it's like it's got a left action by C and a right action by the category D. And I denote this thing like that. I denote it with these triangles and the M and the D, because if you look in here, there's like 3 M's in a row. So you could just kind of consolidate that to the name of the morphism. It's a polynomial. And then C and D are over here. So this is how I denote the morphism. It reminds me that I'm going from M to C composed M and from M to M composed D. So I'll write the bimodules this way. Now, so maybe it looks like this is not so good notation because the maps, it looks like the arrow is pointing right to left, but hold on, because that's actually okay too. Okay, so in Garner's talk, which you can find at this link here, you look up Garner hottest polynomial in Google. Garner explained that the bicomodules from C to D, the CD bimodules, like that we've been writing this way, can be identified with parametric right adjoint functors. If you haven't heard of them, I'll tell you what they are in a second. So these are, I'll call them profunctors from D set to C set. So he showed that those are equivalent. The bimodules in the sense of poly are the profunctors that have been studied for many years by people like Weber and Street and others. So from this perspective, we are going from D set to C set. So the arrow does seem to point here in the correct direction. It points from D to C. So when I think of my bimodules as combinatorial objects, I think of them as going from C to D. When I think of them as functors, I think of them as going from D set to C set. I want to check with you. I want to show very quickly that C0 bimodules is the category of functors from C to set. So let's say D was 0 here. Then what is a CD bimodule? Well, Garner told us that it's a functor from D set to C set, but D is 0. So when D is 0, D set, that means this category of all functors from 0 to set. 0 is the empty category. And how many functors are there from the empty category to set? There's exactly 1. So D set is the one object category. And so we're saying that bimodules, C0 bimodules, can be identified with parametric right adjoint functors from 1, to C set. But it turns out that every functor from 1 to C set is a parametric right adjoint. So we're just getting C set again. So in other words, C set, like these cofree sheaf categories, C set are bimodule categories when we just put a 0 there. Okay, so when I call these profunctors, you may have already heard of something called profunctors. And I invented the term profunctor because it says parametric right adjoint functor. Okay, that's pretty nice. And because it generalizes profunctor. So what's a profunctor from C to D? Some people might say it's a functor from C opt times D to set. And that's what I usually say too. But I'm going to move things around. It's a functor from C to D set op. Now, why do I want to do it that way? Because D set op is the free limit completion of D. If you want to take any category D and freely add all limits, you use D set op. So a profunctor, unlike a profunctor, it doesn't just go to D set op, it goes to the free coproduct completion of D set op. So I'll tell you how to think about this concretely when we get to applications. But but this is what a profunctor is. It's a parametric right adjoint from like this. It's a functor from C to the free coproduct co-completion of D set op. Now, you might not know what a framed bicategory is. And in that case, don't worry, because we're about to go to applications next. But for those who do, the category of polynomial comonoids, which are categories, and the cofunctors and the bicomodules form a single structure called a frame bicategory P. And it's got a lot of structure, including two monoidal structures plus intensor. It's got all sorts of stuff. And it's not actually that hard to think about. So here, let me just describe C mod D in general for categories CD. D0 bimodules, we said, were D sets. These are just functors from D to set. 1D bimodules are the free coproduct co-completion of D set op. And CD bimodules are functors from C to 1D bimodules. So I already told you on the previous line what that is. So it's just kind of D set, and then it kind of ops and free co-completes, and then functors. So there's some layers here, but it's not too bad. The layers are all very categorically nice. So now let's kind of take a breath and start over in some sense and look at just applications. So a Moore machine is something a computer scientist would talk about. And they would say, if you have two sets A and B, then an A-B Moore machine is like a black box. And inside that black box is some activity. So what is it? Well, there's a set S, and we'll call the elements of it states. And every state reads out, there's a function that takes a state and reads out a B. That's called R, just regular old function. And there's also a function that takes a state and a new input A and gives us a new state. And we'll call that update. So it updates the state given the input. We'll furthermore say that the Moore machine is initialized if it has an initial state, if it has some chosen element S0 in S. And so A will be the input set and B will be the output set. Okay, so why is this a machine? Because an A-B Moore machine like this, states, readout, update, and initial state, will transform streams to streams. So let's say I have a stream of A's, A0, A1, A2, A3, and A. Let's inductively define, we already have S0, let's define Sn+1, the n+1 state, to be the update applied to the nth state and the nth input. So we inductively make new state S1, S2, S3, and let's let Bn be the readout of the nth state. So B0, B1, B2. Now we get a list or a stream of B's. We turned a stream of A's into a stream of B's by updating the state. So that's why it's called a machine. How does this have to do with polynomial functors? Well, a machine is this S to B and S times A to S. And that's exactly, sorry, I'm having trouble with my computer here. That's exactly the same as a map of polynomials from Sy to the S to By to the A. You can just check it that, like, when you look at what a map of polynomials is, it gives you exactly the readout and the update. And we could add an initialization by mapping Y into Sy to the S here. One of these will pick out an initial state S0. But this tells us we can generalize. I mean, it turned out what was really making this work is that Sy to the S is called the state comonad in functional programming languages. It's the times homojunction, if you know what I mean, as a comonad. If that doesn't make sense to you, don't worry about it. It's just that this thing is a comonoid in poly, and that's what's making this thing like do the stream transducer stuff. What's making this work, this A's to B's thing work, is the fact that Sy to the S is a comonoid. Now, what is allowed to be generalized is this By to the A. That By to the A could be replaced by an arbitrary polynomial P. So instead of Sy to the S to By to the A, I could look at Sy to the S to P for an arbitrary polynomial P. And what that will do is it'll keep moving around into different positions. And in every position, there'll be some directions that might come to it. And given a direction, it updates its state. So if in every position you had the same set of possible inputs, then you would be a monomial, By to the A. But if different B's, if different things here, different positions might have different inputs, then you get a more general thing. So you could imagine that sometimes you're in a tunnel, or sometimes your eyes are closed. And in those cases, the inputs you get are different. So what it says is every state gets a position. So when instead of an output, you can think of that output as the position that the thing is in. When it's outputting hello, it's in the position hello. But now more generally, for any position, you might have a different set of directions there. And now the update says for any direction I get, I'll take a new state. So these are more general sorts of dynamical systems, but again, we could do initialization the same way. And then slightly even more generally, we could use cofunctors from sy to the s to an arbitrary category C. When we take our old thing of polynomial maps from sy to the s to p, that would be, in this more general version, sy to the s to the cofree comonoid on p. I'll tell you what that is a little later. But the point is, here's the general picture of like dynamical systems that include a very specific case of the Moore machines. So imagine we have a bunch of dynamical systems interacting together. We have P1, P2, P3, P4, P5, and they're sending each other data like this. What's going on? Well, here P3, every box in here, P1 through P5 and Q, they all represent monomials because we're in this kind of Moore machine picture. And so P3 represents the monomial C times Y to the AB, A times B. And this whole interaction, this whole wiring diagram phi is a way that P1 sends its outputs to P2 and P3 and all sorts of stuff like that. And this whole thing is captured by a map of polynomials from P1, tensor P2, tensor P5, all the way to Q. And what does tensor mean? The tensor of two polynomials, what are its positions? Its positions are pairs of positions, one in P and one in P prime. And what's its directions in a I prime? It's the directions of P in I in positions directions of P in position I times the directions of P prime in position I prime. Okay, so it's very simple formula in some sense. We're just multiplying and multiplying. And we can put these dynamical systems or these interfaces P1 through P5 together and get a map to Q. And now if we fill each of these with a dynamical system, sy to the s, s2y to the s2, s3y to the s3, we could tensor all those together and get a dynamical system in Q. And so this picture here, this phi, is a map of polynomials. But more generally, we could have something like a company that can change which supplier it's getting from. So it can either get it from supplier 1 or from supplier 2. And both suppliers are just outputting W and have no input. And the company is inputting a W and is only allowed to choose which supplier it wants, 1 or 2. And so we can get this whole interaction, not just this wiring diagram, but both of them together with a single map of polynomials that says that when the company is in position 2, it picks from this one, and when it's position 1, it picks from this. It gets its data from this one. So I think I talked about that in another talk somewhere, so I'm not going to go into it, but I'm happy to tell you more about it if you're interested. The point is that the company is unilaterally deciding who it connects to. And if you think about you and getting on Zoom today, your internal state, your dynamics, moving around what positions you can be, put your finger in the position of the mouse that clicked the button that put you on Zoom. And that is the same sort of thing that's happening here. So that made me happy to know that, like, okay, getting on Zoom as an internal state, like something I'm thinking and then connecting, is something that Poly can handle. Now, the word dynamical system, if you look it up on Wikipedia, it's usually defined by an action of a monoid on a set. So if you want discrete dynamical systems, you would use the monoid of natural numbers. If you want reversible, you would use Z, or if you want real time, you'd use R. And a T action of a monoid is S times T mapping to S, satisfying two laws. That turns out to be exactly the same thing as a cofunctor from sy to the s to y to the t. And so it fits the general definition above. So this is a very general sort of dynamical system that includes Moore machines and the usual kind of dynamical system, although it doesn't include things like measurability or continuity. Okay, I feel like I'm going a little slow. I'm not sure, but one way to think, I'm switching directions. Okay, forget it. Now, instead of talking about dynamical systems, let's talk about databases. So databases, one way to think of them is that they're just cofree sheaves. You've got objects. Let's say we take this category C. It's got an object called employee, an object called department. It's got a morphism called works in. Every employee works in a department. Every department has an admin person. And I want to add the equation that, oh, and every employee has a manager. And let's add the equation that if I start with department and I look at the admin person and I see what department they work in, that is the original department. So the math department's admin person works in the math department. And this whole thing sketches out a category or presents a category. A functor from C to set, in other words, a C0 bimodule, I, is called a database instance. And what it does is it assigns a set to employee, maybe the set heart, T star star star, and orca. Just random things. I made up random words here. And for department, I assign a set, blue and P9, random things. They're unnamed, they're just identifiers. And the works in, this thing, if I have a functor from C to set, this arrow becomes a function. It becomes a function from employee to department. So it assigns employee heart, it assigns P9, it assigns to this thingy here, blue, and orca assigns blue. Okay, and then the requirement that if I start with blue and I look at the admin person, T star star star, and I look where they work, it's blue. So that's what a functor is. And that's like a database. It has a bunch of employees, a bunch of departments, and some relationships between them. But someone could complain and say, where's the data? How come the employees don't have names? How come it's all meaningless identifiers? So they're correct. You do need that. And so let's include attributes like that P name is, the first name of heart is actually Alan, and this guy is Danny, and orca's real name is Sarah, and blue is the sales department, and P9 is the IT department, information, whatever. So to do that, we assign that every object like C and department gets a set like string. And then there's a canonical cofunctor from C to obc. You might think it goes the other way around, but cofunctors are kind of weird. They go backwards on morphisms. And the data, the attributes, assigning heart to Alan, et cetera, is this alpha here. And this whole diagram is taking place in the frame by category, or the double category, if you prefer, of categories, cofunctors, and bimodules. Okay. The frame by category structure of P is also useful in databases, not just because we have these cofunctors, which we needed on the last slide, but also data migration functors. Those are the parametric right adjoint functors. Those are the profunctors. So a profunctor can be understood as follows. It's a functor from C to 1D bimodules. And what's that? Well, a 1D bimodule is a formal coproduct of formal limits in D. And what's a formal limit in D? It's called a conjunctive query. So a profunctor from 1 to D is a disjoint union of conjunctive queries. And a functor from C, a profunctor like this, is a functor from C to that thing. All right, so let's call a disjoint union of conjunctive queries a DUC query, a duck query, just for simplicity. So a duck query, a disjoint union of conjunctive queries on D, I'll give you an example. Let's say D is this 3-object category. Cities are in states and counties are in states. A duck query might be, give me all the cities, pairs of cities that are in the same state, all the cities and counties that are in the same state, and all the pairs of counties that are in the same state, and add them together. And that's a duck query. So that's kind of the bread and butter of databases. And these bimodules say, I want a C-indexed duck query on D. That way we can move all of the data on D to data on C. And that's why we call it a data migration functor. So now that I've talked about all these different applications and things like that, again, I'm taking one up on his on his invitation to be a little more speculative, since other talks I've given were just more math. So you're welcome to go look at those. But today I'm going to ask a couple questions. One is about aggregation. So one of the most important uses of databases is aggregation. And that is completely absent from the previous story. So the setup is, imagine every employee is paid a salary. I get $5 and Bob gets $10. And everyone works in a department. So we both work in the math department. And okay, now assign to the department the sum of its employees' salaries. Very easy. It should be $15 for math, right? But this is called aggregation. It's not a row by row operation. It's rolling up the entire table. And I don't know of any nice applied category theory story for this in a way that works well with the rest of the database story, the functorial data migration stuff. Now, I thought when I got to Poly, and it was so good at doing things over and over again, like adding things up, I can do that. And it's so good at databases. I thought, oh, well, you're good at these things. Now do aggregation for me. And I tried to find where it could do aggregation. But even if to do aggregation basically means you start with a commutative monoid in the types. So that means salaries are an integer, say, or salaries are a real. And we give ourselves a commutative monoid operation like plus or max. And that's how we do aggregations. But even if I give myself this data, I didn't know how to use it to actually do aggregation in Poly. Poly didn't seem to give me a natural way. Now, this is my current, everyone may have their own version of what the #1 problem in ACT applied category theory is, and probably no one will agree with me besides myself, but I agree with me that the #1 problem in applied category theory that I want to see solved is to understand aggregation. Because for me, aggregation is a crucial step in understanding what summarizing is. I mean, the word sum already is there, right? But summarizing is what we do before we make any decision. We sum it up, we figure out what the actual things we need to do are, and then we make our decision. And whenever a CEO of a company, and I'm using that to represent decision maker, whenever a CEO of a company is using a database, they don't ever query, they only aggregate. They want to know how many units were sold, what's the net, what's the average, what's the graph. They always roll up the tables and summarize it, and that's what they want, and that's what any decision maker wants. So if we're going to be summarizing, I don't know if metaphysical is the right word, it's a pretty big word, but it seems to me that summarizing things is one of the most human and maybe animal, like the Gestalt type thing. Taking a lot of stuff and making it simple is very, very important. So I'd really, really like to understand aggregation in whether it be in Poly or just general in the story that involves data migration. I'd really like to understand aggregation. But I want to get to metaphysics. I know it's a big word. I don't mean it to be a big word. I just mean how we understand the fundamental principles. It is a big deal, though. So it's like, how does time work? How can we, when I was in my 20s, I would hang out with people and ask these kinds of questions, and everyone gets tired of it because we don't make any progress. But I think with the right math, we can make progress. So what's going on with identity, like the ship of Theseus, where you keep changing the floorboards, but it keeps being the same ship? Or what is life? These questions, we stop asking them because we don't make progress. But I think there are ways that we can point at Poly and consider some of these questions and actually be saying things. Whether we think they're true or not is a different story, but at least we can be formal while we're talking, or semi-formal. So what I'm going to say next is just a play of forms. I'm just going to show some signs to you, like tarot cards, but I'm submitting this for your review. If you can tell me whether you like it or not. So I'm not trying to present facts. Well, first I'll tell you about cofree comonoids, but then I'll talk more freely. So one thing we didn't talk about before are the comonoids in Poly. Well, those are categories, but for any polynomial P, I can take the cofree comonoid on P, and it's a category. So which category is it? Well, it's actually a free category on a graph. So that sounds boring maybe, but the graph is extremely interesting, often uncountable, like the first uncountable cardinal. It's pretty big, but not huge. And I'll tell you about this category CP. So it's the vertex set of it is the graph of this graph is the set of P trees. So P is a polynomial, And by a P tree, look at this thing down here. Let's say your polynomial is 2y squared plus 1. So let's say we have green and yellow, and those branch twice. And we have red, and that has no branches. So a P tree is just one where you can put anything you want at the end of an arrow, but if it's green, it should branch twice. And if it's yellow, it should branch twice. And if it's red, it should branch 0 times. And I did a very particular one. In my P tree, of which we take every possible P tree are the objects of this category. But in this one object, what it is that whenever we have green, it branches to green and yellow. Whenever we have green, if we go left, we get green. If we go right, we get yellow. If we're at yellow and we go left, we're back at green. We're happy. But if we go right, we stop. So green, yellow, red, like a traffic light. This whole thing, with all of its rules, is one object in the cofree comonoid. And the morphisms coming out of this object are the paths, the finite paths. So there's a morphism from this big P tree here to this P tree here. This P tree here starts yellow, but it still is a P tree. Wherever you see yellow, there's a branch. Wherever you see green, a branch. And wherever you see a red, it stops. And so a morphism from this to this is this path. So the morphisms coming out of a node are all of the different paths in that tree. Okay, I basically said everything on here. The identity arrow coming out of here is the path to itself, the root node. There's a path, etc. Okay, so why am I talking about this? Because this will give us some intuition. So suppose that you, or the world, okay, you can be in P of 1 many positions. Your body can be in P of 1 many positions, or the entire world can be in P of 1 many positions. That's P. And for every position you could be in, P bracket I, many things might happen. One of these P bracket I things is going to happen to you. And your character, who you are, how you act, is how you respond in each case. This character here, always when he's in green and he gets a left, he moves to green. And when he gets a right, he moves to yellow, etc. But your character, you're in any one of these positions. And when things come and happen to you, you respond by going into a new position. And that's the way you are. So P is like your body, and your character is CP set. It's this topos of all dynamical systems with interface P, all the different flowcharts for what you would do given some things that happen to you. And so we can describe our characters, namely the character of the world, like physics, or the character of you, using the internal language of this topos. It says, what ways do you know how to respond to inputs? How do you move from position to position based on inputs? And then in my last couple slides, I'll use that to talk about experience, like what's up with that. So again, I'm just giving you some things to think about. They're not true. They're just ideas from the math that the math says, hey, take a look at this. So imagine this about experience. So right now, the past is irrevocably gone. It's gone forever. And it's always now. It's now, right now. If you're listening to this, it's now. So all we have of the past is what's left here in the present. So this includes the layout of your surroundings. You're looking at a computer right now because someone put the computer there and you put yourself in front of it. You have a chair, all these things. The layout of your surroundings is all that's left of the past, including the layout of your mind, your memory, the current position of your mind, which is your current memory, plus everything in the world is all that's left of the past. So when you find a dinosaur bone or anything that was, it's in the present, it's in the ground now. And there's nothing left of the past except what's in the present layout of your mind and reality. And so what we have to do, and what reality is always doing, is continually consolidating the experience. So you're in a position right now, and something's happening, and now you're in a new position, and now you're in a new position, and now you're in a new position. And so all that remains of the past is the present position. There's nothing else. And so what's happening now is the present direction. It's what's coming into your senses, given where you are. And so imagine that our job is to compress the past into the present. Since the past is irrevocably gone, the only way we're going to remember anything is to compress it again into the present. So to take wherever you were, whatever you're thinking about now, and deal with the incoming information to be in a new state. And the way you do that is your character. Your character is your way of compressing the new data you have with the position you're currently in to be in a new position. The way you do that is your character. And that, I call it compression because we have to encode both the old position and the incoming direction into a new position. So we're constantly consolidating over and over the old position where we are right now with what's coming in to get the new position. And so our character is the type of ways we respond when things happen to us. Okay. So moving forward, what I talked about in my abstract was what I'm calling the AI transition. And that is that humans, we try to mimic intelligence when we see animals and people using it, right? When we see animals doing an interesting thing like bird song or something, we try to understand it. And so even computers, those were originally people. Everyone talks about that, but maybe we forget sometimes. So computers were people, and Alan Turing explicitly in his paper used these computers as people. He used them to think, what are they really doing? And he designed Turing machines to mimic their behavior. And so humans, we're always trying to mimic intelligence and jam it into artifacts. And that's why we call it artificial intelligence, because it's an artifact that encodes intelligence we see in the world. Now, once we encode it into artifacts, we can run them very, very fast, all the time, all night and all day. And when we run all we understand about intelligence in the world all the time, it makes things very, very complex, more and more complex. And so I think the complexity of the world, when you look at, say, what happened in the US on January 6th, or what happened with GameStop in the stock market, or COVID, all sorts of things, the complexity is increasing. And I think that's going to keep happening. As we understand more and more about how computers and intelligence work, there'll be more and more complexity because the artificial intelligence, in other words, what we encode, will be running faster and faster, or more and more, trillions of times more than it does when it's just people with no computers. But I think this gives mathematicians a place they can enter, because if we understand something in constructive math, we can make technology out of it. And if we say it in an elegant way, then the technology won't be ad hoc. Ad hoc means for a purpose. Elegant is kind of like more general purpose. So I would prefer to be alongside elegant AI rather than ad hoc AI. And so I think mathematicians can join this historical moment. And even if they love thinking about math, they can push it a little bit to the, a little bit closer to reality and start to lead the way in making elegant constructions of the way we see intelligence in the world, in an ecosystem, or in the way that an organization works. We can start to encode the truth, or the not truth, but what we're seeing there, as best we can, and make elegant AI. So Poly for me is an entry point. I like it. It's familiar and comfortable to me. But I invite everyone, and maybe you were already joined, but here we are in this historical moment. It seems to me we don't have much time, maybe 25 years before we hit some kind of ecological collapse, whatever you think it is. I think it's time to get on board and start using our math for good. And I think there are ways to do that. And I think we're starting to see that category theory is applicable to real world stuff. So to summarize, before I summarize, I'll just say that Joachim Koch and myself were organizing a polynomial functors workshop in March, about a month from now. And we have all sorts of speakers lined up, and you can join. Here's the website. Yeah, that might be fun for you. If you're interested, please join. And lastly, to summarize, Poly is remarkably abundant. It's completely combinatorial, so the calculations are concrete, like y plus 1 squared really is y squared plus 2y plus 1. But it's also theoretically beautiful, like the comonoids are categories, the coalgebras are cofree sheaves, and it's got a wide scope of applications from databases to dynamical systems. I didn't tell you about cellular automata today, but I did in a previous talk. And so it's a single setting for pursuing mathematical and philosophical and technological progress. So thanks for your time.
Thank you very much, David. That was Yeah, really great talk. Thank you so much.
My pleasure.
Well, are there any questions or comments for David?
So I have a question, David. So poly is Cartesian closed, as you said. So if you take two polynomials, what sort of thing do you get when you exponentiate one to the other?
Yeah, good question. Well, well, I'll tell you what y to the y is.
Yeah. Okay.
That's the most interesting one because it's so simple. It turns out to be y plus 1, which is pretty weird, but it's also telling you it's not a completely trivial operation. If y to the power y is y plus 1. But in general, p to the q, well, q will be a sum of monomials, so you can at least break that apart. And in my book, I should have advertised this book here, but I didn't. But in a book that you can find on GitHub, and I'm happy to send a link, it gives the full formula if you're interested.
Okay, thank you.
Yeah, thanks for asking.
Yeah, thank you, Bob. Yeah, Carlos has a question.
Well, maybe really thank you for the talk. I appreciate really how you manage these ontological questions about how works the time and what is life. But as you are working with polynomials, I don't know if it is a question. Is how is the role of algebraic geometry here? So you can use, for example, these results, the Nullstellen sets and that kind of thing.
Yeah, good question. I thought about that for a little while. So let me tell you some things. First, there are no negatives here. It's all non-negative. If we add negatives freely with some kind of int construction or Grothendieck completion of this category, then we lose a lot of the plus stops being a coproduct and time stops being a product, and so we lose some stuff. I also don't know what zero sets mean. See, polynomials form a category, not just a set. So we would have to know if I take the zero set of one polynomial, even if it has negatives, and the zero set of another polynomial, if I have a morphism between those polynomials, what should that tell me about zero sets? I don't know. So a lot of the structure, there's not enough structure, it doesn't have minuses, and there's too much structure, it has morphisms instead of just elements. So I don't know what exactly we can get from algebraic geometry, but it's certainly intriguing. The only thing I do think about, the only thing that did make sense to me is these guys here. There's a ring theoretic direction, and that's from C to D. And then in terms of, I feel like in terms of affine spaces, it goes from D to C. So that part feels right. But other than that, that's the only place where I got any intuition from algebraic geometry. But I'd be very happy if someone had some idea of what the Nullstellen or any other algebraic geometry thing could mean, given that we have so many morphisms around.
And David, and is there any relation with this Laurent phenomena in quivers that you mutate and then you have this? This was the positive conjecture that you have only polynomials with positive coefficients. Yeah, I don't know if you know about that.
With quiver representations, I didn't hear the question exactly.
There is a way to generate cluster algebras with quivers, and this has some sort of polynomials that in the numerator you have only polynomials with positive coefficients, and you create this by mutation. And then it's really interesting. There has a lot of combinatorial structure. And
oh, that sounds very interesting. I have not thought about it at all. Yeah. Yeah, it'd be interesting to think about that. maybe I can ask you afterwards or something, or for more information.
Yeah.
Thank you, Carlos. Are there any other questions or comments? Mauricio, yeah, you can.
Bueno, ¿me puedes ayudar a traducir?
Sí.
Bueno, sería una pregunta más sobre metafísica. ¿Qué ventajas ves en tu sistema a otras alternativas para hacer metafísica en matemáticas, como lógicas para consistentes o reales no bien portados, como reales también basados en lógicas para consistentes?
Bueno, a ver, poquito a poquito, porque creo que no puedo traducir todo tan rápido.
Sí, no.
So this is a question in Spanish, so I'm translating for Mauricio. I'm sorry, Mauricio, perdón. Entonces, so Mauricio is asking a question about the metaphysics and this model and the poly model for metaphysics. And so, yeah, sí, Mauricio.
Sí, ¿qué ventajas tiene su sistema con respecto a lógicas no para consistentes?
Lógicas no para consistentes?
Para consistentes.
So Mauricio is asking what are the advantages of the sort of poly model for metaphysics with respect to what? ¿Cómo era otra vez?
Lógicas para consistentes.
Para-consistent logics. Yeah, what's the advantage?
I don't know what para-consistent logic is.
So, well, bueno, pues sí, nos puedes explicar un poquito qué.
Sí, son lógicas que aceptan contradicción como parte de la lógica.
Okay, so these are logics that accept contradictions as part of the logic.
Okay. I don't know. So what's going on is these, for example, in this dynamical systems thing, where you have these flowcharts, okay, and then there's logic in the sense that these are always toposes, and toposes have an internal logic. But that kind of logic is telling you about how the characters, you might have a character who's like this and a character who's like that, and we can and or. And it's not at all about paraconsistency in terms of how these characters are seeing the world. I know I'm not probably answering your question exactly, but basically, if we wanted paraconsistent logic, it's probably that the actual character themselves, like the you or me, has in their mind how they're going to behave given various inputs. And as the inputs come in and they change their position, the way they do it is with some kind of maybe paraconsistent logic. They have their own internal way of seeing how they should behave, and that's their character. And so maybe for every paraconsistent logic, there exists a character, something in the internal logic of C sets. That seems possible, but I don't know enough to say.
Okay. ¿Puedo preguntar otra?
Sí.
Bueno, y también la pretensión metafísica que tiene Spivak también es tan fuerte como decir que toda la matemática se puede describir con esta teoría.
¿Cómo? Perdón, otra vez la puedes.
Ajá, sí, que si su pretensión es poder describir toda la matemática con esta teoría.
So Mauricio is asking if pretensión como objetivo o.
Sí.
So is your goal to describe? ¿Me podrías preguntar otra vez? Perdón, Mauricio.
Sí. Sí, es complicado. No, que si toda la matemática se puede describir con esto.
So if is the goal to describe all math as poly things, I guess.
I don't think it's it's to describe as much as is good. Only what's good. So for example, these cofree sheaf toposes can be described here, but general toposes cannot, I don't think. So sorry, someone's yelling in the background here. I don't think we can get all of math into poly, but we can get a lot of it, and we can get some of it, some of it. Maybe we can start talking about measurability or probability. Maybe not. We can see how far it goes. but it's a very, it's a single category that has a lot of structure to it. And it seems to be good at talking about things that I consider interesting applications, but we can't take it further than it can go. So I'm not trying to jam everything into it or fit everything into it, but as much as is comfortable.
Yeah, thanks.
Yeah, thank you.
Muchas gracias, Mauricio. Perdón por la traducción tan mala, pero, so Omar has a question. Yeah, please go ahead.
I remember hearing talk about these categorical databases years ago. You had besides this cofree sheet, that one was visual sets, and the advantage was that could handle missing data.
Oh yeah, missing data.
Sorry.
Yeah.
Can you hear me?
It's a little bit,
And,
yeah.
So I was wondering, can so is there data with?
Yeah. Good question. I would say that this is not as good at handling missing data, or I don't know how to. I wouldn't say it doesn't work. I just don't know how to do it. So yeah, good question. Yeah, an older version of this stuff did have missing data. It was simplicial databases, I called them, but this is, I guess, I mean, this subsumes that in some sense, and yet in another sense, it doesn't make missing data a foregrounded thing to do.
Okay.
Yeah. I could explain more, but I'm afraid that for people who don't know that background, it wouldn't be easy to explain it in a way that both satisfied you and made sense to people.
Oh yeah, that's good. I just wanted to know if it was covered in some way.
I would say not yet, not with this description I gave here.
Okay. Thank you.
Yeah, thanks, Omar.
Thank you, Omar. Are there any other questions or comments?
Yes, I have a question.
Yes, please.
Okay, so you show us morphisms of polynomials with corolla forest. I don't know if you can show us an example of doing that, doing a morphism of polynomials, but using bundles. I don't know if you have one example.
Yeah. So let's say I have two bundles, P and another one, Q. Then what you do is you go from the base space of P to the base space of Q with a function. And then you pull back the Q bundle along that function. And you get something here, and you map that to this bundle, kind of like schemes. So if you know what a scheme is, you have the underlying topological space, you give a map from, if you have a ringed spaces or something. So you have a ringed space X, OX, and you have a ringed space Y, OY. Do you know ringed spaces?
Yeah.
Okay, so it's a map from X to Y and a map from F upper star OY to OX. And it's the same thing here. So we get a map on the base space of the bundle, we pull back the total space, and we map it to this one here.
Okay, thank you.
Sure.
Thank you very much. Yeah, the morphisms are, yeah, in that context, they're very beautiful. Yeah, are there any other questions? Yes.
I am interested in bundles. That's why the question.
Yeah. So if you want the bundle maps to go forward on the base and forward on the total space, you get something called Dirichlet polynomial. Instead of y squared, you would get 2 to the y and stuff like that. So so you can go forward, and use Dirichlet polynomials, or you can go forwards on the base and backwards on the fibers, like with ringed spaces, and then you get the category polynomials. So both
Thank
sorts
you.
of bundle maps make sense. Yeah. Sure.
Sorry, there is kind of noise here. But do you have a bibliography when I can like study those stuff?
It's a good question. I don't offhand, but if you send me an email, I'd be happy to answer any questions.
Oh, thank you.
Sure.
Yeah, I'll send you an email.
Great.
Thank you very much. Are there any other questions or comments? Yeah, there's another question. Yes, please.
Yeah, so this is Fred Quintanar, and so you've discussed how poly is used with dynamical systems, but this recent discussion about bundles and going, I guess, different directions, maybe covariant and contravariant. I was wondering actually whether you could relate the modeling dynamical systems with state space models, which are, I guess, I'm actually thinking of an approach to state space models which has, I guess, types above and tokens below, and you can have covariant functors. So this has something to do with, I guess, true construction, true spaces.
Mm-hmm.
But anyways, I'm just interested if you've thought about how state space models for dynamical systems might fit in with this whole approach using poly.
Well, I don't know what exactly you mean by state space-based approaches, but here we do see something I'm calling states, and we use the states with poly. It's all poly maps, S, from S to B and from S times A to S, and also dynamical systems in terms of monoids acting do have a polynomial description, but in terms of choose spaces. A colleague of mine, Di Gerardo, just gave me a functor from Chu to from the category of choose spaces to the category of polynomials. It sends like a choose space. If you have A, B, omega or something like that, it sends it to the sum over A and A of Y to the sum over B and B of omega AB. So I don't know if you can hear that.
Okay.
I said it very quickly, but there is a functor and there is a monoidal structure on Chu that acts like the tensor that I use here. So there's a strong monoidal functor from Chu to poly, and for one of the monoidal structures on Chu.
That sounds very interesting.
Great. Yeah, again, if someone has questions or ideas, please send me an email. I'm happy to, tell you more or hear your ideas, etc.
Thank you very much. Are there any other questions or comments? Yeah, I don't want to take too much of your time, David, but do you have could you expand a little bit more on this, on aggregation? So maybe explain it in some other contexts, or so maybe in this idea of characters as CP sets or something like this. So how to
yeah, I don't know how to do it in terms of like the characters of the me and you and all the people aggregating things.
Okay.
But in terms of just database aggregation, just imagine you have a table full of data points.
Yeah.
X, Y. And so you have 43 rows of XY pairs.
Yeah.
And someone wants to do machine learning, or someone wants to do linear regression, or someone wants to do something with all that data, an average or a count or a whatever. That's called aggregation, where you roll up the whole table into one thing.
Yeah.
And that's a fine thing to do. If you have a monoid, you can, one monoid could just be multisets. So you can just take all of your data and throw it into one big multiset of data. And that is an aggregation.
Okay.
And from that thing, you could then draw a graph or do anything you want. And so, if we have a monoid, we can do aggregation. The problem is, what does aggregation have to do with the rest of the structure of databases, data migration and all that sort of thing? So if I want to do queries and I want to do aggregation, how do they fit together? And I just don't know.
Okay.
And then you said, how does it fit with like this metaphysical issue of life and all that sort of thing? And I'm saying it's summarizing. But again, since Poly has these two views of like, it does seem like we're constantly summarizing, what did I say here? We're constantly compressing the past into the present. That feels like aggregation.
It feels a lot like aggregation. Yeah.
Yeah. And so I'm just like, this should work out. This should work out. This should work out. And yet, whenever I bring pencil to paper, I don't know how to make anything happen. So I think it's a problem I keep throwing myself at, but I'm coming from a very particular direction. So if anybody, I think it's something that anybody could work on. It's fairly low barrier to entry.
Yeah, it sounds very, well, I don't know. It sounds very crucial to this idea of summarizing the past, or summarizing things into experiences or whatever in the present, and then going forward, maybe having this observation of, and well, so technically, well, I don't know. Well, maybe this is again speculation, but yeah, I suppose the technique from databases. I don't know, but so it looks very nice and very exciting, and
especially if someone figures it out.
Yeah. Well, I mean, exciting and thinking about and figuring it out in the end.
Yes.
Yeah. Well, there is a question on this, and I suppose you've talked about this, and you already mentioned there's no the intention is not capturing everything, but in the cofunctor picture of dynamical systems, is there any hope of getting some sort of more structure into your dynamical systems, like continuity or whatever?
Continuity. Maybe. I haven't looked too much into that. So if, let's say you have a cofunctor into the reals here as your monoid, then it does mean that what it tells you is, if you're in a state and I tell you move forward 2 seconds, it will tell you a new state. If I tell you move forward 1 second, it'll tell you a new state. And from there, if I say move forward again 1 second, you'll get the same thing as if you move to 2 seconds to begin with. So if I say, where are you after 1 second, you can tell me, and then I can subdivide that into half and a quarter and an eighth. And what happens in the first half and then the second half does equal what happens over the course of one whole second. So there's some kind of arithmetic continuity, but it's not, but it could still vibrate wildly as you move closer and closer to zero. And so, you very well might want, so in some sense, this tells you the integral of the vector field rather than the vector field itself. If you want to actually have a differentiable vector field, then you might be able to do it using polynomial functors. Don't just exist over sets. They exist for any locally Cartesian closed category. It's called, I think you might just need pullbacks or something. You don't need all that much. And so, and so maybe if you look at topological spaces instead of set, then you'll get all the structure you want. I just haven't looked into it.
Okay, well, thank you.
Sure.
Well, are there any other questions or comments? Well, if not, let's thank David. Thank you very much for the great talk.
Well, thanks for having me.
Very happy with it. Extremely happy. Yeah.
Happy to be here.